So this is the second installment of our binomial theorem lesson. And in this lesson, we're going to look at a couple of sort of almost like puzzle type problems that I think you'll find really fun. So one of them is working out the number of roots through a grid. And so if we have a starting point and a finishing point, and everything is built in uniform blocks the way it's shown here in the diagram, then the problem is to figure out how many possible different routes can you take from start to finish. So one of them is depicted here in the red dotted line. So we could start obviously at the starting spot and then move along to, I need a different color, move along to the finish in a number of ways, and this is just one of the ways. I could go all the way across the bottom and then up the top. I could go all the way up first and then across. And then to figure out exactly how many different ways there are, I think it would be pretty exhausting to have to multiply or draw them all out. We are going to look at this from the point of view of a combinations problem. So we have 6 blocks going, I guess what we call east and west or in the horizontal direction. We have 5 blocks going north and south or in the vertical direction. And so if we look at it in terms of one block at a time and the number of ways that we can navigate through those blocks in terms of a pathway from start to finish, then there's a couple of different ways to look at this. One of them would be to look at all of the possible solutions, almost like one of those word problems that we were doing before, like how many different ways can you rearrange the word or the letters of the word mathematics. And so we would start with the number of letters in that word as a factorial, and then we would divide out the number of repeating letters because we can't tell EE apart from EE. It doesn't matter which E we're putting first and second. And so in this case, we can't tell which N we're putting in order from another combination of N, and so on. And so if we have 11 different blocks of either north or east direction from start to finish, then we could look at that as a word with 11 letters that we're rearranging in 11 factorial ways. But then we have to take out the repeats, which would be 5 factorial and 6 factorial. And so that's one way to look at a problem like this, is to do it like that in terms of like a combination type problem. And then we would work that out and find out the exact number of roots that exist. 462 is the total number, and I'm glad we didn't draw all of those out because I'm sure you have better things to do with your time. And so we know now that there's 462 unique routes that we can take from S, the start, to F, the finish. Okay, so here's another example of the same kind of question, but this one has a little bit more of a twist to it. So we've got 2 different starting points described here. We have a starting point, A and B, and the finish is way over here in the top right corner. And so if we're only allowed to travel east and north, according to the question, then let's look at A first. If we start at A and we can only go east, which is to the right, there's 5 blocks that we can travel in that direction, and there's 5 blocks that we can travel in a vertical or northern direction. And so with 5 north and 5 east, that gives us a total of 10 factorial that we could arrange if repeats were allowed, if we didn't have any repeating letters in our pattern. But we do have 5 repeating N's and 5 repeating E's, and so we would have to divide by 5 factorial in order to get the final answer in this case. That gives us a total of 252 ways that we could travel from point A to the finish. So that's going to be different if we now take a look at B as our starting point. And so if we start at B and we can only go east or north, then there's a total of 6 blocks that we can travel east, but only 2 that we can travel in a vertical direction. So we have 6 E's and we have 2 N's. So that's a total of a combination. If we're looking at it as like letters of a word being reorganized, there's 8 letters to reorganize. And so we can take 8 factorial, but we then have to divide by the repeating letters, so 6 factorial, 2 factorial in that case. So if we start at point B, there's less routes to go because we have less distance to travel, so that makes sense. There's only 28 routes. So from A or B, remember or in statistics and probability means plus, right? It means to add the 2 totals. So we have 252 ways to get from A to the finish, and then there's 28 unique ways to get from B to the finish, and so the total number of routes possible in this problem is going to be 280. These problems are really, really fun. These are the checkerboard problems, and we've got our checkerboard, our red checker on the board, and we have to figure out the number of different paths that this checker could possibly take if it can only move diagonally 1 square at a time. So what we're going to do is fill in the blank spaces as we go along, figuring out, almost like Pascal's triangle, how many different routes are possible, and then sometimes we have to add the routes diagonally down because we can come at it from both directions. So, for example, if I start with my red checker, then let's take the red checker and move it diagonally towards the left, and there's only one way we can do that. If I do the same thing, only I go diagonally in the right direction, there's only one way to do that, and those are the only 2 possibilities for getting my checker from the first row to the second row of the board. Now, if I continue going out, this is going to look a lot like Pascal's triangle. In the left diagonal direction, I can only move to this square in one way. There's only one route that my checker can get there. The same thing in the right-hand direction. There's only one way that I can get out to that next diagonal in the next row. However, in the middle, and here's where you're going to recognize this as Pascal's triangle, there are 2 ways that I could get there. I could have gone like this, or I could have gone like that. So there's actually 2 possible paths. If my checker landed there, I wouldn't know which of the 2 paths I could possibly have taken. So we're going to continue on. As we go out in the diagonal way, we're going to always fill in our 1s in the diagonal. And because our checkerboard has a limited number of squares, it's not going to look exactly like the Pascal's triangle. It's going to be a little truncated on one side. But when we work out the middle numbers, we're going to remember that we always have to combine the number of paths in the previous row to get the total in the next row. So here I've got 1 path on the left, 2 paths on the right, so there's a total of 3 different paths that I could take to get to that square. And the same thing in this square, I have 2 and 1 that lead to 3 paths to get to those squares. So this is going to be very much, like I said, like Pascal's triangle when I'm filling in my squares as I go down. It all depends on how the checkerboard is set up in terms of where your first checker is, and your numbers might change slightly. If we keep going, 1 plus 4 is 5, 4 plus 6 is 10. This is looking a lot like the 5th row of Pascal's triangle, isn't it? This is the 5 choose. However, I'm going to put just a 4 here because my diagonals are cut off and I don't have anything to add on the right-hand side. So as we keep going, that's going to continue. There are 5 ways to get to this square. Now there's 15 ways, 20 ways, and then 14 ways. So we're going to diverge a little bit from the pattern of the Pascal's triangle because we're missing those 1s on the ends of our diagonals. If we keep going in the final row, there's 20 ways for us to possibly land in the first square, 35 ways to land in the second square, 34 ways to get to the third square, and still 14 for the last one. And so the number of ways that we could possibly travel from where our checker started to one of the possible spots in the very last row on the other side of the checkerboard is 21 or 35 or 34 or 14, which means we're going to add them all up, and so we're going to end up with 80, 90, 91, 96, 100, 104 different possible ways to get that checker to the other end of the checkerboard. We're just going to go back to the same worksheet that we had for lesson 1 on this topic, and we're going to do the other questions that we couldn't do before. And so 3, 4, 5, 6, and 7 are all questions that will give you more practice on what we just talked about.